Hi everyone, my name is Andrew Chalmers. I'm a postdoc at the Computational Media Innovation Centre, or CMIC for short, at Victoria University of Wellington. Today I'll be talking about a paper titled Illumination Space, a feature space for Radiance maps. The motivation behind this work is regarding image-based lighting, which is a rendering technique that uses Radiance maps, as you can see here on the left, as a light source to render to light scenes. As you can see on the right, this right image used the left image as a light source. It provides high quality, realistic lighting that matches the real world environment. These Radiance maps are actually growing in databases. So there's public asset databases, privately owned and sold databases. There's also databases in studios that are used internally. And there's also academic databases where different universities and research groups are collecting Radiance maps and sharing them for research purposes. The motivation behind collecting these databases, there's a few reasons. One is in machine learning, where you have a large collection of these light sources, Radiance maps, and you pair them with cropped limited field of view images, and then the goal here is to then estimate the environmental lighting from a limited field of view image. This is useful for mixed reality, augmented reality applications. There's also another area, look development, which is more on the artist's user-friendly artist side. We can see here on the right with Unity, they have an interface where they have a small set of Radiance maps, and then in their panel they have a 3D object, and they need to evaluate their object and different assets and textures and things under different lighting conditions. And so they'll evaluate it under this collection of Radiance maps and make sure that it looks good in each condition before they send it off for production. The challenge is then, how do we organize a Radiance map database in a semantically meaningful way? With traditional light sources, as the ones that you see on the left here in Maya or Blender, such as your point light, direction light, area light, they have easy to use parameters that control the properties of these lights, such as the direction, area, intensity. However, Radiance maps are just pixels, and there is no concise description that controls these Radiance maps. So the challenge is, how do we get these low-dimensional features out of them that are easy to use from an artist's perspective? Prior work looked at semantically organizing regular photographs rather than Radiance maps, and this was not focused on lighting. This was also later extended to then account for HDR environment maps, but was still focused on the textural properties of the environment map rather than how the environment map affected the rendered scene. In terms of rendering, there are spherical harmonics, but these are not artist friendly and intuitive to use. And then in 2008 there is the SRBL specification, but this is just a specification which describes desirable attributes to organize a database, but it doesn't define a method of doing so, nor is it exhaustive in terms of the features required. To address this challenge, we define and extract a small set of dominant and ambient lighting properties for every Radiance map in the database, and we convert that into a semantically meaningful 5D light feature vector. This defines the illumination space. We also have a user interface called Illumination Browser, which takes those 5D vectors and visualizes them in 2 scatter plots, allowing artists to visualize and browse through the database. To do this, we have a light feature definition and extraction stage, where we go through an unorganized Radiance map collection, extract the dominant lighting properties, parameterize those, and as well as we also parameterize the ambient lighting of each Radiance map. This results in 5 features for each Radiance map. We then visualize the Radiance map database by plotting each Radiance map using its 5D feature vector in 2 scatter plots. This not only visualizes the database, but also allows artists to interact and browse through the database. The first stage is light detection, where the aim is to find dominant light sources in the Radiance map to then parameterize. This has to be automatic to run over a database, and we want to detect only the most important light sources in the Radiance map. The first stage is to create a rendered image, which is a cylinder on a ground plane observable from a top-down perspective camera. We then convert that to a complete shadow profile image and then threshold shadows that are not perceivable from the human eye. The goal is then to select pixels from the Radiance map that only contribute to the perceivable shadows. This effectively gives us the most dominant light sources that created those perceivable shadows. This results in this mask here. To do this, we first take superpixels from the Radiance map and then select only superpixels that contribute to that perceptible shadow profile image. We render them one at a time, starting from the most bright light source, and render each light source at a time and check if it contributes to that shadow profile. If it does not, then we reject it and keep going until we come up with a small set of superpixels that contributed to that perceivable shadow profile image. We then fit a parametric model to each of those dominant light sources. This is a spherical Gaussian, an anisotropic spherical Gaussian, so you can see we can squeeze the light source and also rotate it. This is quite powerful and can describe a wide range of light sources, including this face that I made. Here's an example, a real example. We've got this Radiance map and we've picked out those dominant light sources and fitted these anisotropic spherical Gaussians to those. We then can convert this to a dominant light model, which effectively converts it from a light source, a description of a light source, to a description of how it looks in terms of a shadow, like how soft the shadow is and how long that shadow is. The end result is that we have a set of dominant light sources and a model that fits each one. We then infer a small set of features, F, sigma, theta, and C, from those models. Effectively, sigma and theta is the size and elevation of the most dominant light source, and FC summarizes the effect of multiple light sources. The features here, FH and FS, are the hue and saturation. We get this by taking a Radiance map and rendering a diffuse plate and taking the hue and saturation value from that diffuse plate. The end result is the illumination space, which is on the right here. We take the dominant features and the ambient features and plot them in two scatter plots. The top is the dominant features in 3 dimensions, X, Y, and then color value for Z, and the hue and saturation in the bottom scatter plot. Here is the Illumination browser interface, where we can see on the left is the illumination space scatter plots. In the center are the returned results based on where you click in the illumination space, and on the right is a rendering preview based on what Radiance map you select. Here we can see we're going to turn off the ambient lighting features and focus on dominant lighting only, where we're going to go up in the elevation feature and then move to the soft overcast lights before moving back to the sharp low elevation lights. Turning back on those ambient lighting features, we can see all the tones and dominant lighting match now, and now we're going to move through the hue and saturation, going from red tones back through the whites and to the blues. Now we're going to move back over to the overcast Radiance maps, select one of those, and we can see that in that preview rendering window. We evaluated our illumination space in a couple of different ways. First is through database query, where given an illumination space created from an existing Radiance map database, and then given a new example of Radiance map, we query that database and see how similar those two results are. So on the left is the input, on the right is our illumination space method, the returned most similar result to the input, and on the right there is the prior work's most similar result using their texture features. You can see ours matches the illumination much more accurately, where on the right, far right, is the cylinder rendered scene, and you can see the illumination matches quite well for ours compared to the input. We also did a user evaluation where artists used our tool to find a Radiance map from the database to match a target photograph. The artists then evaluated how easy it was to use the features and how well they could match that photograph. See our paper for the results. Overall, it was very positive. So to conclude, we define and extract a small set of dominant and ambient lighting properties, which runs automatically over a database. We then convert those properties into a semantically meaningful 5D light feature vector that defines the illumination space. We also introduce the Illumination browser, which is a user interface that takes that illumination space and visualizes it in a UI, which then artists can browse and select and apply the Radiance map to a preview renderer. Future work could look at sparsity in the database, introducing more parameters, as well as integrating our illumination space into other systems that look at using tags and the textured content of the Radiance maps. Thank you for listening, and feel free to ask questions or send me an email.